Hi everybody, welcome to our second remote lab. This one will be lab number 10 for Physics 180, and we'll be going over torque and rotational equilibrium. Again, these pre-lab lectures are just to give you some background, a little bit of taste of the equations you'll use, and introduction to the material. Please still use your lab books as the instructions and the document I provided. But let's dive into the pre-lab lecture. So, everything in physics so far, you might not realize it, but everything so far has been a point mass. When we provided a force, or we measured the energy of a mass, it didn't matter if it was a car, or if it was a roller coaster, or a pendulum. It just mattered that we pushed on it with some amount of force to get it to move. So everything could have been simplified down to a point mass. Today, though, we're going to, for the first time, work with a real two-dimensional object. And when you have a real two-dimensional object, you can move it side to side with forces. You can translate it. Yeah, good geometry words in here. Translate. Again, don't spell with the pen, David. You can translate the object, but now that you have a real two-dimensional object, you can also rotate it. You can push on it in some way that will cause the object to rotate. So we've got a new kind of movement, and of course physics is interested in describing how this new movement occurs. So can we describe how an object rotates? This is especially important when you're worried about balancing something. If we put this on a balance, you want the rotations to cancel out. You want it to be balanced on here so that one side ends up more massive and gravity doesn't pull it down and rotate it. So torque is super important if you want to get good at some party tricks. Here's one of my favorite party tricks. You can get forks balanced on the edge of a glass with a toothpick. And it's really cool because you can even burn away the toothpick and it will stay balanced. All has to do with the center of mass of the forks. That the forks have a lot of mass between here and here on the handle, and that can cancel out the weight on the head. So the center of mass is right on that brim of the cup, and the torques are balanced out. So we have this equilibrium where it's balanced on the edge of the cup, which is pretty cool. He shows a different angle here too. Alright, so how do we do the physics here? We've worked with translational equilibrium. Translational equilibrium. That was when the sum of the forces is equal to 0. We knew if all the forces going one way equals all the forces going the other way, the object wouldn't move. The same way, we can have rotational equilibrium. And to measure rotational equilibrium, we need this new quantity called torque. And it's when the sum of the torques is equal to 0. We represent torque with a tau here. So how do you measure torque? You might already have an intuition about balancing things. When you balance things and you push it, it matters where you push it. If you push it here or push it here. And it matters how hard you push it. So torque is equal to the force applied times the distance, which we're going to call this the lever arm distance and denote it with that little perpendicular sign. So this is lever arm distance, which is the distance from the pivot point. That's important in this lab. It's the distance from the pivot point, from wherever the force is applied to the pivot. The units of torque are Newton meters. You know, force is in newtons, distance is in meters. Now, Newton meters, we've actually seen them before. They're actually joules, but torque is not an energy. And that has to do with the force is perpendicular to this distance vector. They're actually different directions. So we're going to keep this as Newton meters. A torque is measured in Newton meters. And we know an object is at rotational equilibrium when all the torques are equal to 0. And just like in forces, when we said all the forces one way equal all the forces the other way, we can do that same thing with torques. We know when the torques clockwise equal torques counterclockwise. There's a ton in the book about which one of these we call negative and positive, but just like in forces, it just matters on which way we define it. So as long as torques going one way is equal to torques going the other way, then they cancel out. So what's some examples of torques? When do we rotate something by applying a force to it? Might think about that. I've had the answer of doors before. Door is a good example. And door stops. Putting a door stop in a door, we've all struggled with it. It's all a game of equaling out the torque from the door with the friction on the ground, where we're going to apply that lever arm to equal out that torque. Another example is a seesaw. Seen one of it? Alright, we're going to see some meter sticks like this today though. But we saw a seesaw, or in the Midwest, we call them teeter-totters. They don't call them that here, but we call them teeter-totters. Funny word. Teeter-totters. And you have your two friends on there, and as long as you're equal mass, you can get it going back and forth. As long as one person wasn't too massive, they had more force, so it was much harder to get it balanced. I always did the thing where you like stand in the middle. That's always fun when you're a kid. Stand in the middle and try and balance it out. And it's all a game of how far you're away and how massive you are. My favorite example of torques is actually wood chopping. I've got this video of these axe wielding. When you're chopping wood or hammering, you should know this with hammers too, you want your hands all the way at the bottom of the handle in order to maximize that lever arm. So you're going to get more torque, you're going to be able to slam into that wood harder if you have a larger lever arm. Now when you're hammering, you might realize that the further you go down on the hammer, the further you choke back, the more force you get. But you also have to balance out your control on the hammer. So when you swing an axe, the way you're supposed to do it is when you go up. Oh, I missed it. When you go up on the axe, you're going to miss it.
3, 2, 1, go!
you slide your hand up in order to maximize your control on the axe, and then you slide your hand down to maximize the torque. So this is pretty funny. Watch these guys chop this wood.
Shepler and Adams are tied for place 4 and 5 at the minute, and both guys setting off at a really fast rate. The time to beat, 27.09 seconds, and there's nothing between them. Ooh, this was close on the turn, but it looked like Adams just about managed to turn first. This is such a close heat. Adams is through.
The announcer is so excited. Now these are two guys that understand torque and how to maximize it to chop into that wood. One last example, I showed you how bad I am at sports last lecture, so I'll show you how bad I am at cars this lecture. Horsepower is equal to your car's torque times its RPMs, its rotations per minute. So if you want to compare cars and get the most horsepower, you can maximize the torque or the rotations per minute of the car. So that leads to a bunch of articles like this that I don't understand at all. 7 ways to increase your vehicle's horsepower. And you do weird things like cold air intake. I don't know half these words, but I'm sure one of you guys is a car guy. And this is all about maximizing the larger diameter. It's maximizing that force on your axle to get the most horsepower in your car by increasing the torque. Alright, that's the intro to torques. This is going to be a shorter lecture than the last one. Here's the lab that we're doing today. We have this pretty simple setup of this balance. Up here, what's attached to the meter stick is called a knife edge clamp. You're going to see that word a lot, knife edge clamp. And we've balanced a meter stick on this support and hung 2 masses. And we want to get this thing in rotational equilibrium or balanced. We see this one is closer to the clamp, and this one is further away from the clamp. So you can kind of think about it. Think about balancing an object. Which one is more massive if this is balanced? Yeah, this one has to be more massive. So if distance goes down, the mass has to go up to balance out this torque. And we can see that with the equations. We know this is in equilibrium, so the torque clockwise equals the torque counterclockwise. This one's pulling clockwise. This one's pulling counterclockwise. So we know the force times distance 1 equals force 1. Force 2 times distance 2. This is D1 and this is D2. And what's providing the force in this lab? Simply gravity. It's just mass times gravity is our force. So we have mass 1 times gravity times distance 1 equals mass 2 times gravity times distance 2. We see here that gravity cancels out, and we get this ratio of mass 1 times D1 is equal to mass 2 times D2. And we could use this to find an unknown mass. Like if we didn't know mass 1, we could find it by just doing mass 1 is equal to mass 2 d2 divided by d1. Or we could put it in a ratio formula. One last way, let's put it mass 1 over mass 2. The ratios of the masses equals the inverse ratio of the distances. Easy equation, and can actually be pretty intuitive. That you have to, if you increase the mass, you have to decrease its distance to keep it balanced. That's all this equation says. So this is part 1 of today's lab, this top setup. In the second table today, you're going to see part 2 of the lab is a setup like this. We've moved the pivot point and put a mass on there, and it's balanced. So what's balancing out this mass? We've got a force over here, so we've got a torque times distance 1, mass 1. What's balancing out this mass on the other side? Well, it's a meter stick itself. The mass of the meter stick is now balancing out this mass on the other side. Here, we set it so the pivot point is exactly at the center of the meter stick. Center of gravity can be a really scary term and can be really hard sometimes, but sometimes it's really easy. Center of gravity is just the center of the object when it's linear density and irregular shape. So if this has the same, not linear density, constant density. If this has the same density throughout and it's 1 meter long, then the center of gravity is at 50 centimeters, right in the middle. So here, the center of gravity of the meter stick is still at 50 centimeters. This is the center of gravity. Of the meter stick. And why we care about the center of gravity in physics is we can treat this whole object as a point mass at its center of gravity. So this whole mass is, you can think about it as canceling out on each side, and it's just equal to one force down, the force of the meter stick at this distance away. And we're going to call this d naught, distance. So remember about that lever arm, that the lever arm is the distance from the force to the pivot. So it's the center of gravity, which we're going to call xg, minus the pivot. The lever arm distance is the center of gravity minus the pivot point, xp. And here we've got the mass of the meter stick times gravity. And the mass of the meter stick we're going to call m naught. So the equation is actually the exact same. You have m naught over m1 is equal to d1 over d naught, the inverse of the distances. Same equation, just a different setup. We now have the meter stick providing the torque on the other side. That's it for the lab today. It's a pretty short one. The next 2 labs are much longer. Be prepared for that. But let me know if you have any questions by email. Thanks for watching. I'll see you next lecture.